All right, so this is chapter 3, lesson 4, proofs with perpendicular lines. So pretty much all we're dealing with today are perpendicular lines and how we can use them. Okay, so the first thing that we're going to do in this lesson is to find the distance from a point to a line. So the distance from a point to a line is the length of the perpendicular segment from the point to the line. It is the shortest distance between the point and the line. So let's draw our own example given this. So the distance between the point A and the line K is the distance between A and B. So if we have any line here and then any point, okay, so let's take this as our point. Now, it's saying that the distance between this point and the line must be a length that makes a 90-degree angle with the line. Okay, so this is the distance from the point to the line. Okay, and so we're going to do an example. Example 1, find the distance between point A to line BD. So obviously point A is up here. And now, in order to find the distance between A and the line BD, which is this one right here, we have to find which segment makes a 90-degree angle with the line AD. And that's this segment right here. So AC is the distance we are looking for. So AC, we want to find the measure of line segment AC. In order to find that, we have to find the square root, remember, the distance formula of, and we'll label this one x1, this one y1, this one x2, this one y2. So we're going to do x2 minus x1, which is 1 minus -3 squared plus, and then y2 minus y1, which is -1 minus 3, and we square it. So the measure of AC, sorry, that's not how we write it. Okay, so that's not how we write it. You should just write it as AC. Remember, the measure, the M comes with angles, not with line segments. That's my mistake. Okay, so we're going to write it as the square root of 1 minus -3 becomes 4, because it's 1 plus 3 squared, plus -1 minus 3 is -4 squared. So we're going to get that the distance between A and C is the square root of 16 plus 16, which is the square root of 32, which is the square root of 16 times 2, which is 4 square root of 2. So the distance from point A to line BD is 4 root 2. Okay, perpendicular bisector. So something called a perpendicular bisector. It's the perpendicular bisector of a line segment, PQ, is the line N with the following properties. So if we're looking at the line segment PQ down here, that's the distance from here to here, okay? It's going to be line N, and N is perpendicular to the line segment PQ, as you can see. At point M, it forms a 90-degree angle, which I just boxed in black. And it also passes through the point M, which is the midpoint of PQ. So it makes the distance between P and M equal to the distance between M and Q. That's what we call a perpendicular bisector. All right, proving theorems about perpendicular lines. So a linear pair perpendicular theorem. If two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. If the measure of angle 1 is the same as the measure of angle 2, or angle 1 is congruent to angle 2, then G is perpendicular to H. That should seem pretty simple, right? Because any line, the measure of that line, a straight line, is 180 degrees. You divide that in 2, then you should have two 90-degree angles, right? So if both of those angles are equal, then they're both 90 degrees. Our lines are perpendicular. Okay. The next theorem is proving theorems about perpendicular lines, the perpendicular transversal theorem. So in a plane, if a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other line. So if H and K are parallel and J is perpendicular to H, then J must also be perpendicular to K. Now let's go ahead and prove this, okay? So we know that this is perpendicular. So J is perpendicular to H, and it makes a 90-degree angle. So what tells us that this angle must also be 90 degrees? And what tells us that is the corresponding angles theorem. It says that if that angle up top, the angle between the intersection of J and H, is 90 degrees, then the corresponding angle down below, since H and K are parallel, must also be 90 degrees. Proves this theorem. You could have also said the alternate exterior angle theorem, because we could have said that this angle is also 90 degrees by the alternate exterior angle theorem, and that would have also proven it. So you could have used either one. All right, proving theorems about perpendicular lines. So the next theorem is lines perpendicular to a transversal theorem. In a plane, if two lines are perpendicular to the same line, then they are parallel to each other. If M is perpendicular to P and N is perpendicular to P, then M and N must be parallel. Okay, so if you have a line that's perpendicular to two lines, those two lines are going to be parallel. In other words, if your transversal has two 90-degree angles, those two angles, the lines that form them, are parallel to each other. Okay, so the photo shows the layout of a neighborhood. Determine which lines, if any, must be parallel in the diagram. Explain your reasoning. Well, let's go ahead and take a look, and let's define which ones are 90-degree angles. So we know that this angle, and this angle are all 90 degrees. So we can determine that some of the lines are perpendicular. So I see that S and P form this intersection up at the top left. So we can say that S and P are perpendicular. So since P is perpendicular to S, and I see that not only is P perpendicular to S, but so is Q, because I look down here and I see that Q is also perpendicular to S. That forms a 90-degree angle. And Q is perpendicular to S. Then P must be parallel to Q by the lines perpendicular to a transversal theorem. Okay? Now, there is one more example that we can use. So let's take a look. I see that S is perpendicular to Q, and T is also perpendicular to Q, looking at this, right? So we've got our second one, I'll put it in red. Since S is perpendicular to Q and T is perpendicular to Q, then S must be parallel to T by the lines perpendicular to a transversal theorem. Okay, and this was our last example today. So all right, good luck. Next slide. This is not your homework. Go ahead and check Canvas for your homework. This is not your right assignment. Okay. Your homework is posted on Canvas.